discuss a different problem. It is the problem about the quantum advantage. What does it mean, quantum advantage? Okay, let's start with step by step. So let us consider all the problems that you can imagine in quantum computation. You know, a lot of people study this kind of problem, several different classifications were made. So for us, in this moment, we need a classification based on the complexity to solve the problem. One of the main class in this kind of classification is called class P. What does it mean? It means that for classical computer, we are in this moment that everything is classical, we know at least one quantum algorithm that scales polynomially with the dimension of the input. The most simple example, you have to consider the sum. The sum like that we do just from the elementary school. So we take two numbers, we take before the unity, then the second digit, the third digit, so on and so forth. Obviously, as long as the number, as long as the number of steps that we do, and so on. In this case, we have a linear incremental complexity, but so we have an algorithm, a series of operations that we have to repeat, and the dimension, so the number of steps that we need to solve the algorithm is a function of n, and in this case, the class of problems is polynomial, is scaled polynomially with the dimension of the system. That's the first class. Then there is a second class, that is the class MP. A lot of people say MP is non-polynomial. That is wrong. It's not like this. So MP is a different class of problem in which we say, okay, there is a problem. I imagine that there is a solution, and I can check the solution in polynomial time. So in a time that scales polynomially with the dimension of the input. So the typical example is the factorization. Suppose that we don't know absolutely that 3 times 5 is equal to 15. So we say, 15, we have to find the two prime numbers that which product give this number. But we don't know how to do it. But we made some analysis, and we have the hypothesis that the solution is 3 and 5. And then we can check it in a polynomial time using the typical algorithm that we do from the elementary school, that 3 times 5 is equal to 15. And again, this algorithm, so the algorithm which we made the product, scale polynomially with the dimension of the system. So instead to have 3 times 5, we have 300 and whatever, 323 plus, and the other number is 111. Then obviously we need more time, but this time if you do it, scale polynomial. If you do it, or if your computer do it. So it's really an open question up to now that if there is a relation like equality or inequality. So there are people say, no, P and P must be the same, but there are people instead that claims that these two classes have to be different. Up to now, we know for sure several problems for which we know that we can test the solution in a polynomial time, but we haven't an algorithm that is able to solve in a polynomial time. Again, this is the problem of factorization. So factorization, if we have so suppose that we have a number that is a product of 2 prime numbers, and we have to find what is the 2 prime numbers. there are several algorithms, but all these algorithms has an exponential time with the dimension of the system. Obviously, if we have a solution, we can test the solution instead of polynomial time because the product is much faster. This seems not so relevant as a problem, but take into account that probably if you are able to find an algorithm that is able to factorize a number into prime number in a polynomial time in a classical computer, you will become rich in a few seconds. Because you can break almost all the security of all banks that you want, and you can take all the money that you want from the bank. Because I don't know if you knew it, to give an idea, in general, not always, but a lot of security system works in this way. So when you put username and password, there is an algorithm that associated to your username and a prime number. There is another password that associated to there is the same algorithm associated to your password, another number, another prime number, and then you take the product of the two. So it's easy, it's very fast for the computer to make the product, and then but the computer does not save the two numbers; it saves only the result of the product. Because the result of the product, once you have this number, to find the two numbers that compose username and password is extremely complex. So there is this trick in the difficulties. So in one way it's very easy, in one way it's very complex that allows to make security. So if you are able to break this game, you become a billionaire in no second. And probably after then you go to the jail, but it's another problem. Okay, joking apart. So now there is another class of problems that are interesting for us. That is this B2B problem, whereas B is a bound error quantum polynomial. So does it mean that there is so there are algorithms that are able to quantum algorithm that are able to solve a problem in a polynomial time with a bound error. This means that with a quantum computer, if the solution that you obtain is close, so it's a solution that you obtain, and the true value distance between these two is always less or equal of epsilon, where epsilon is a number that you can take as small as you want. Obviously, smaller is the number, longer is the process, but still the process, one that you fix is the error that you consider your limit, then this the number of steps that you need for to solve the algorithm increase polynomial. So why this is important? Because we know, for example, the algorithm Shor, we know that there are problems that with quantum computer, they fall in the BQP class of problem. Instead, when we are in a classical computer, when we use a classical computer, they are NP, but they are not in the P class. So their solution can be checked very fast, but the solution cannot be found very fast with a classical computer. At least the problem of these things is always that, especially for the class P and NP, that once that you find an algorithm to solve a problem, you know that the problem is a P. But until you don't find an algorithm, there is no way to prove it that there is no exist any algorithm possible. So in some way, once that you fall in a problem fall in the P class, it's fine. But until your problem is still not in the P class, it's still an open question. So, but this is for the factorization problem. We have the Shor algorithm. The Shor algorithm is on in this BQP class of problem, but the Shor algorithm works in for the factorization. So to find the factorization of of a number in two prime number. But when you do with a classical computer, this is not in the P class. So obviously, one way it can be interesting to study the Shor algorithm. Shor algorithm is a long process, it's extremely long, extremely complicated. I don't want to enter too much in the Shor algorithm, but I would like to show something different to make an example of how it works and how is the reason because the quantum computer can solve some algorithm in a more efficient way. So let us do a different problem, much easier. So suppose that you have a function that is defined in the ensemble 0, 1. So the argument of the function can be only or 0 or 1. And the result can be only 0 or 1. So extremely simple. And you want to understand if not the value of the function, but only if the function in 0 and the function in 1 have the same value or the opposite value. The thing that you are asking you always this. So is this function constant or this function is not constant? You are not asking anything else. So if you have a classical computer, you have nothing else to do that you take the first input, you evaluate, see the value, you put the second input, you evaluate, and see the value. So you have to do 2 times the algorithm. Then you compare, and then you see are equal or the function is constant, this function is not constant. But let's see if with the quantum computer we can do it in a faster way. So the idea is, okay, let's try in this way. At the beginning, we consider the state 0, 1. So we consider to have 2 qubits. 1 qubit we put in the 0 state and 1 in the 1 state. At this point, we apply another gate on all the 2 qubits. Other gates is a gate that can be written in this way. So 1, minus 1, 1. Sorry. So when you can check it, when apply Hadamard gate to 0, what we obtain is plus. So the against Hadamard gate applied to 0 is equal to plus, that is equal to 1 square root of 2, 0 plus 1. And instead, when I apply Hadamard gate at 1, we have like minus, that is 1 square root of 2. One. Okay. So at this point, we apply Hadamard gate, and what we obtain soon after applying Hadamard gate, we obtain the state plus. Or that seems easily be more comfortable for us in this moment is 0 plus 1. Now we apply our algorithm. So our algorithm, we can write this algorithm in this way, consider as a unitary function like that. If we have the state 0 x, no matter what it is x, and we apply, we obtain something that is 0, and then we have x plus f0. This plus with the circle means that we are making the sum modulus 2. So 0, 1, 0, 1, 0, 1. So 1 plus 1 is 0, 0 plus 0, 0, just 0 plus 1 is 1. And then applied over 1 is nothing else than 1 x plus f of 1. So let us apply this algorithm to this situation. Sorry. I believe that I have closed it instead. It's still. Sorry. So let us apply this function to our state. What we obtain. So let us apply to 0. So U0 minus. What happens is that we have U0. We have 0. And then we have square root of 2 just here. 0 as 0 plus f0 plus 1 plus f0. Now, what happened is that if f0 is 0, this is still stays 0, and instead this one stays 1. So this is if f0 equal to 0, this function becomes a0 minus. If f0 instead is equal to 1, it becomes 0, 1. This becomes, oh, sorry, this is a minus. This is a minus. 1 plus 1, it becomes 0. But this means that there is the minus state with an opposite, with the sign changed. So we can bring back the minus outside. So what we obtain is f1, if f0 is equal to 1, we obtain the state minus 0. Analogally, with the same, exactly the same steps, we can evaluate 1 minus, that is 1 apply also square root of 2, 0 plus f of 1 minus 1 plus f1. And this is again the same situation. If we have f0, f1 equals 0, this is again 1 minus. If f1 is equal to 1, we have minus 1 minus. So we can write these two cases in a simple way, like minus 1, the f of 0, 0 minus. And this one, the state here is minus 1, f of 1, 1 minus. So the same, putting all together the stuff. Putting all together this stuff, we obtained this, this new state after the second step is 1 square root of 2 minus 1 f0, 0 plus minus 1 f minus 1 f1 1. Okay, that's now it seems that the trick, but the idea is that we have obtained the two phase factor here, one here, which so the value of this phase factor depends on directly on the function that we want to understand if it's constant or is not constant. And you see that there are only two possibilities. If the function is constant, no matter if it's +1 or -1, +1 or 0, that's not so relevant, because the only thing that it goes, if they are constant, they gives only a phase factor just in the beginning, but this state becomes directly the state plus minus. On the contrary, if the two values are different, there is a relative sign between the two, no matter if this is positive or this is positive, because in the worst case, it's only a phase factor just in front of the full state. It does not count. So we obtain the state minus minus. So again, at this point, last step is that I can make Hadamard transformation. So at this point, I can discard the second qubit. We'll have it here, but theoretically, we already discard. We made an Hadamard gate on the first qubit. So in this case, this becomes 0 minus, and in this other case becomes 1 minus. So now, if we make a measure, if the function is constant, we obtain the state. So we will, if we make the measurement, so we will obtain the eigenvalues associated to the state 0. Instead, if we have made if the function is different between f0 and f1, we obtain this state. We make a measure, and with certainty, for sure we obtain the state 1 minus. So we obtain this state. As you can see, with only a single measurement, you were able to obtain the same result that with a classical computer you need to have two measurements. Okay, it seems not a huge advantage, because you say, okay, yes, we made an increment, for sure, so we were faster because we made only one measurement and not two, but so there is not an exponential increment. That is the thing I want to say, but the idea that we used in this process is exactly the idea that is behind the largest part of the algorithm that show quantum advantage respect to the classical one. So the idea is that playing with the state, playing with, especially with the initial state, with the superposition principle, here is put from 0, 1, in which there is no superposition. You made an Hadamard and put a state that are both the two qubits are in superposition. This allows you to evaluate the algorithm on the whole system simultaneously. So instead to work on each single input times by time, you can work on the whole system, and this means on all the possible input of the system simultaneously. This sort of huge parallelism, quantum parallelism, is one of, not the only one, but one of the main reasons for which quantum algorithms usually are better than classical algorithms. For some problems, because to be honest, there are not for problems that are in BQP class, but for which there is no algorithm from in the P class. In this situation, this can give you this kind of approach can give you a quantum advantage. Oh, now one can think, okay, that's great. That is work perfectly. So the way every time that I have a problem, I do this trick, and so there is clearly a quantum advantage. So I can use a quantum computer for always to beat a classical computer. This means that in another way, that means that if I have a classical computer, I can never simulate efficiently a quantum computer. What does it mean? So what does it mean that I can make an efficient simulation of a quantum computer? So one point is that, for example, is that I need to store all this. So if suppose that you have a quantum state. One thing that you want, if you want to work on your computer in a quantum state, you have to store the problem. You have to store the state. But a state, a quantum state, if it is defined of number of n qubits, then the state can be written, a generical state can be written like Cn n, where n is a generic or complete basis for our Hilbert space. But these numbers here, so they are complex, and especially there are 2 to the n different coefficients. So you immediately see that, so if you have a classical computer, if you want to, as soon as you go to 20, 24, 25 spin, that's, you cannot imagine, and you cannot store anymore. You can do some tricks. If your state, there are some symmetries, you can reduce a little bit, but you gain a factor of 2, 4, or something like that. That, okay, it's a qubit more, but does not change the picture. So you are extremely limited. Not only that, the point is that since you have also a huge number of input, so when you start to a number of input that increase exponentially with the dimension of the qubit. So when you try to evaluate, you try to run your algorithm, this means that your algorithm has to run on a number of data that are not, that does not scale with the number of qubits, but scales with the number of the coefficients, to scale exponentially with the number of qubits. This makes that all these quantum algorithms are extremely complex to be simulated in a classical computer. I made a mistake. Is yes or no? So yes, in general, quantum algorithms are extremely complex to be simulated on a classical computer, but not all. There are a class of quantum algorithms, a class of quantum states that are relatively easy to be simulated. And these also, this class, as you will see, are extremely interesting because they can be also, they show why entanglement is not enough to explain the quantum advantage. So, the class of state that you want to discuss is the stabilizer state. So let's start step by step also in this case. Let's do with the, let's try to start from, okay, Pauli group. What is the Pauli group? Okay, everyone knows what are the Pauli matrix. So we have sigma 0, and sometimes in a computational paper you can find that with I, sigma x that you can find with x, sigma y that equal to I, and sigma z with z. Okay, and then now imagine that you have a number of n of qubits. Then you consider this, the Pauli string as the example of that normally is indicated in this way. So what does it mean? It means that we consider a string made by n operator. All the operators are one of these 4. The first act on the first spin, the second act on the second spin, the third act on the third spin, and so on and so forth. So for example, if we have n equal 3, so for example, a typical string can be z, z, y. That is a string. This is almost enough, but is not still enough, because to have a clear quantum a group structure, we need also not only to consider that, also we have to extend the Pauli group, taking into account also the global phase. So we consider the Pauli group is like an element that can be 1, -1, I, minus I, tensor, yeah, times I, X, Y. So this means that together with this, we can also consider the operator that, for example, is minus I, and then the same stuff. So, okay, this is the Pauli string. Now, let's start to go towards the state. We consider a stabilizer state defined on an n-qubit Hilbert space, like a state for which there exists a particular string for which the state C is equal. So in which our state is an eigenstate of the Pauli string with eigenvalues equal to 1. It probably will be not a surprise that if we have a number n of qubits, if we have one Pauli string for which our state is eigenstate with eigenvalues equal to 1, there are several others. We can prove it that the number of Pauli string for which, so given a state that satisfies at least for one Pauli string this relation, we can prove it that there are a total of 2n different element of this that is called the stabilizer group of the state psi. The important thing is to observe that you can define a complete set of n, not 2n, but only n elements of the stabilizer group that have the property to commute each other and to be linear independent, that can act as the basis of the stabilizer group. So to give an example, not trivial example, let's imagine the state psi that is equal to this typical 1 square root of 2, 0, 0, 1, 1. This is a stabilizer state. The stabilizer state for the operator that are ZZ, XX, minus YY, and the identity. But if you consider these two, you can see that it can act as a basis because the product of these two, this by itself gives the identity, the product between these two gives this other operator, and so on and so forth. So it's okay. That is okay. We want to say okay, interesting, but why is these states are so important? Do you want that I prove the Knill theorem now, or we want to make a break and then there is the Gotsman theorem, Gotsman-Knill theorem to prove. So want to do stop now, break now? It's okay. Let's try to go faster. Then we take a break after. Okay, let's. let's try to explain why these states are so relevant. So the Gossman theorem says that if you have if you start from a stabilizer state and you consider an algorithm made only by just 1 second. Made only by Clifford operation. So, sorry, I forgot the word Clifford. Then the quantum algorithm can be simulated efficiently, so in a polynomial time, on a classical computer. At the beginning, let's before introduce what is a Clifford operator. So the Clifford operators are operators that, if we are in an unitary operator, then when act on a polystring, left brings the polystring in a polystring, in another polystring. This is important because what happens that it's trivial to see that if we consider that this relation is correct, let's consider the stabilizer state. We know that stabilizer state has this property. Then if we try to transform this equation with this unitary operator, this is simple U P I, that is U P dagger U I. So we have that this state, the stabilizer state transformed, is again a stabilizer state with respect to a transformed polystring. So now this helps us to understand how the Kneel theorem works. So the idea is that so at the beginning, one of the problems we say that when we have to write down a quantum state, we need to use a huge amount of space. But this can be overcome. As we have seen, each state, each stabilizer state, is made, so it is associated to a group of polystring. So the stabilizer is a stabilizer group. And this group of polystring has the property that can be identified completely by a set of n linear independent operators, n linear independent polystrings. So at this point, we can so the idea is that, for example, to give an example of, so in our state on one example can be identified completely by the state z times identity and identity times z. So we can make a direct connection from the state to the complete set of spin operator of polystrings that define the stabilizer group. So at this point, the idea is that, okay, let's try to see if using this kind of expression, we can reduce the number of the space that we need to summarize, to describe the state. So the idea is that we can, so since it's for each single spin, we have 4 different polystring, identity, Z, X, and Y, we can identify this string only with 2 different elements, ZX, writing if there is if you consider identity, this means that there is no one of them. Identity means no one of them. Okay, if we have Z, this means this will be Z, but not X. If we have X, this means that is Z, not Z, but X. If we have Y, we have both the two, because both the two means that we have made the product, and then we have Y. So at this point, so if we have a polystring made of n qubit, we can describe the polystring with 2 to the with a vector of 2 to the n input, 2n input of the string. So for example, imagine that we have a string like X, Y, Y, Z, identity, whatever. And then we will have something like 1, 0, 1, 1, 1, 1. Sorry, this is 0, 1. 0, 1, 1, 1, 1, 0, 0, 0. But this is obviously this only in is not still not complete, because I have seen for the stabilizer state there is also the phase factor. But the phase factor there are only 4 values, +1, -1, plus I minus I. So obviously we need only 2 qubits more to define if there is +1, -1, plus I minus I. So we have only, so with 2 and plus 2 input, different input, you can describe a polystring. But each single state is, each single stabilizer state is completely individuated by only n different polystring. So if we take 2n plus 2 times n different parameters, we can completely describe the state. So at the first point, the problem so when for a generic quantum state, we need 2 to the n different coefficients, the parameter to describe the state, and moreover, these parameters are also complex, so theoretically, is 2 times 2 to the n, because we have to consider to save not only the real part, but also the imaginary part. With the number, with the for the stabilizer state, you need only something that scale n like n square. Not only that, so this means that you can store the result quite easily. Moreover, we have seen that if we consider the Clifford operators, what we obtain is that we bring strings, polystring in polystrings. So what happens? This means that when I have to apply a Clifford operators to my algorithm, so to my state, the only thing that I have to do, I don't have to evaluate directly the state, but simply apply the Clifford operators to these strings. But this is something that can be done in polynomial time. And this means that also the simulation requires only polynomial time. Not only that, also the measurement works in this way, because the easy way to make a measurement is that you measure directly in the computational base. This means that you have to go in the base 1, 1, 0. So when you have a state, you need to do something like that. You make local rotation and then observe what are the phases associated to this one when you obtain 1, 0, 0, 1. This again gives you polynomial time. So the point is that if I have a quantum algorithm that start from a stabilizer state, use only Clifford operators, and realize and make a measurement in a computational basis. This can be simulated on a classical computer in a very efficient way. It seems from one side this seems really a little bit tricky because okay, it's not so seems very limited in case, but this is a very important consequence because it tells you that you can really simulate entanglement in an efficient way in a classical computer. Not all the form of entanglement, but some form of entanglement. And this implies that entanglement is not. Yeah.
To clarify, you say the state is the state characterized by the generators of the polygons, right?
Exactly.
Every row there.
Yes.
Like
each two rows, each columns, each two columns gives one operator.
Every pair of columns is an operator.
Yes. So let make an example here. For example, so let's take. So let's put, for example, from this one here, we have on the first pin we have Z, so we have 1, 0. The second is the identity is 0, 0. And then here there is the phase, but okay, for here there is no phase, so we have no problem. Instead here we have first operator is the identity 0, 0. Second operator is Z, and so here is 1, 0.
The number of rows is the number of qubits.
The number of rows, there are always two columns because one column is the X and then one column is the Z. And plus 2 because there are 4 different values, so theoretically you can input, so there is 2 qubits that you have. 1 plus 2, but okay, the important scales with 10, they include plus 1 plus 2. So the thing that I want to say, to show you that, to be honest, so look what happens with Clifford operators. Okay, let me put in this other way. Suppose that we start from an operator that is, well, we consider it 2 qubit to make something simple, at 0, 0. Then at first, we apply another AND gate on the second qubit. On the first, sorry, on the first qubit. Another gate applied on the same on the state 0, 0, gives us the state plus 0. That is, if you want, 1 square root of 2, 0 plus 1 by the 0. Then we apply a CNOT gate. A CNOT gate can be written in this way, in a matrix written in this way. What happens in this case is that if we apply this, so this state here can be written this 1 square root of 2, 0, 1 square root of 2, 0, and if you apply, what you obtain is simply 1 square root of 2, 0, 0, 1 square root of 2. That is nothing else than the state that we already well know. So we started from a state that is completely classical, so separable, pure, whatever. We apply another gate that is a Clifford gate. We arrive in a state that is still classical, but with a different basis. And then we apply a C0, and applying a C0 gate, we create entanglement. So even if a state has entanglement, you cannot, you can simulate if the other hypotheses are satisfied in a very efficient way in a classical computer. And why this is important? Because if you can simulate efficiently entangled state in a classical computer, the quantum advantage cannot be related to the presence or the absence of entanglement. And so we have to find something different to justify the quantum advantage. This is quantum difference, the magic, but we will discuss about the magic after the break.
Ask you one question here.
Yeah.
So you can easily efficiently compute the output expectation values on any Pauli operator, right? Like if somebody has stabilized state, you want people, you can write down easily,
yeah.
And from that you can easily compute the expectation values of Pauli observables. Does that imply you can also efficiently compute the output probability distribution and sample probability? Because it's still an exponential number of outcomes, right?
No, the point is that obviously you can have if you cannot have an exponential number of output because the number of operators are finite. So also that goes increase polynomially. So also the output will increase polynomially because it's connected to the numbers.
What outcome means, right? Like still any qubits, you measure the computational bits at the end. Possible outcomes, right? Possible bit strings.
Yes or no. Take into account one thing. You cannot discriminate. So if you have a degeneracy when you make an observation, you cannot discriminate between the degeneracy. Pauli operators are always two different eigenvalues, +1 and -1. So when you made if you want to consider the phases, you can arrive to 8. But every time you have to make a different measurement, you can obtain only this kind of value. Then you can realize a different kind of state.
When I say measurement, I mean you evolve the state evolves, okay? Then I just measure the bit stream.
Yeah. No. So I know that. So the point is, so if you have a state, so you have to consider that this to be efficiently simulated, you need to consider only a measurement on the computational basis, no? So if I gave you a state 1, 1, plus, 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 and then I take a state up, down, down, and that I observe the total magnetization from the sigma z. Is all the total, not the total magnetization, the total correlation is +1 and is +1. So if I observe sigma z1, sigma z2, sigma z3, so a Pauli string.
So maybe the polarizing mathematics like run a circuit, like on a superconducting kind of circuit. At the end, we get number of events for every single bit stream on the processor.
Yeah, but in this case, you are not doing a Clifford operators. You are doing so because you cannot discrete. So the point is that if you use only these operations, you can only obviously. So if you have an observable, this observable, so can be done, can give you only or +1 or -1.
Not saying measuring an observable. It's measuring a POV, projective measurement, which kind of amounts measuring all products of that observable.
Yeah, but so this kind of operator is so if you want to observe an exponential number of operators, this is exponential, not because for the complexity of the algorithm, but because you are doing an exponential number of steps because you want it.
Experiments, every time you get one of the events.
No, this is the same stuff. It's so because you are only saying instead to measure one quantity, I want to measure an exponential number of quantities. This is exponential, but not because the algorithm is not exponential. But a single measure bit is this scheme, or this one or this one. So the point is that when you obtain a measure in this kind of approach, the only thing you obtain is not the state, but the value, the expectation value. So you cannot. So that's the point. So you cannot discriminate. So if I made this observation and I obtain one, I cannot discriminate between this one and this one. Then if I do another different, so I do this, then I do another one, then okay, I can start to, but this means that I'm trying to do something different. So I'm forcing the algorithm to do different steps. And obviously this is increasing, but this is not connected with the number of with the possibility or non-possibility for a stabilizer circuit to realize to be simulated in a polynomial time. Yes. Un attimo, le mani che ce l'ho nere proprio. Vado l'altro, adesso faccio ogni per... C'è bisogno di magic. No, vecchiaia. Can we restart? So, okay, we're seeing that the Clifford operators and together with the stabilizer state that seems to be extremely powerful, but there are a huge limit. The main limit is that it's a way is one of the way because they are powerful. So the point is that when you have stabilizer state and you apply a Clifford gate, you obtain again a stabilizer state. So in a way you can consider that a set of operators in this case is universal if that fixing an initial state, we can define several circuits and then of different operators. So when we consider circuit, normally we consider a series, an ordered series of gates. So if I consider only the Clifford gates, I can construct the circuit, but no matter how long are my circuit, I will always stay in my stabilizer state. And the problem with the stabilizer state, even if they are a huge number, the number of stabilizer state is for a system of n qubit, we have 2 to the n, the product of 4k that goes 1 to n, 2k plus 1. This huge number of, if for n is equal 1, there are 6 that are all the set of eigenvalues of x, y, and z. For n equal 2 is 60, for n equal 3 is 1080 or something like that, then increase. So the number is extremely high. So, but nevertheless, they are not dense. So even you can imagine, you see easily that if you consider that there are, so in 1 qubit, you only have the 6 pin, but the 6 state, but the total amount of states are infinite. This means that this state cannot be dense. If they are not dense, what happens is that I cannot run a generical bound error quantum polynomial algorithm because for sure, if there is a state stabilizer state here, stabilizer state here, any kind of algorithm let me do from here to here, jumping from this state. But if my target is this state, I can never reduce the error less than this distance. So there is really a huge problem with that. So one can say, okay, that is a big limit. What we can do to overcome this limit, one can think, okay, we have to add tons of different other gates. No, it's enough to add only one other gate, that is called the T gate. The T gate is written as this way, 1 T I over 4 yes, yes. Yes. And it's very interesting that it's enough that this simple gate, that is a 1 qubit gate, it's enough to move from a non-universal algorithm to universal algorithm. Why it works? The point that comes out from the non-commutativity of the operators. So imagine that so obviously if you take a gate and you have a number n of qubit, the number of rotation that you can do is limited. But then you can start to play with the T gate and, for example, the Hadamard gate. The T gate Hadamard gate does not commute. So changing the order of T gate and Hadamard gate, you can really create a dense set of state. And this dense set of state allow you to go closer and closer to your target state. So the point is that T gate obviously does not left you in that bring you from a stabilizer state outside this set of state. And for this way, you can start to think about how to effectively to create a resource theory for the magic. So in a way, magic can be considered in a very broad sense. How many? So if you have a state, you have to consider how many T gate I have to add to what is the minimal number of T gate that I have to add to the Clifford circuit to go closer and closer to the state that I'm evaluating the match. So obviously, if the state is stabilizer, I don't have to add any of them. So the total magic is 0. Instead, going further, going always more and more distant from the stabilizer state. This means that I have to increase the number of T gates that I need. So let us discuss a little bit of how to write down a resource theory for magic. The resource theory of magic is, again, in all these 4 lessons, we always follow the same path. We won't change for the magic. So when we have to introduce a quantum resource, so we have to introduce at the beginning a set of free state. In this case, it's very easy. The set of free state is a stabilizer state. There state that does not need any T gate to be produced. So you can start from the standard initial state, so all 0, and then using only stabilizer state, you can obtain your only using Clifford operation, you can realize your stabilizer state. Then you need an operation. You need something that brings free state in free state, and also this one we already seen is the Clifford gate. Since Clifford gate left Pauli string in Pauli string, that's also a perfect candidate to be the operation that left the free state in free state for our resource. And if you check it, effectively the stabilizer state does not increase the magic, does not increase the number of T gates that you need. So since it's simple to see, because obviously in the Clifford gates there are no T gates, so realizing a Clifford gate does not increase the number of T gates that you are using. So the state that we obtain is exactly the same state as the number of T gates that is exactly the number of T gates of the state from which you started. So that's exactly, so this allows us to create a perfect theory of, perfect resource theory of magic. And magic can be seen really as the amount of resource that you need to create to quantify in a way how difficult is to create to realize a quantum algorithm. There is, however, a problem. So so our target is that we want to understand where is what is the reason of the quantum advantage? The point is that we can do something very simple. So imagine that we can write down, so we have a state, we organize the state following this kind of plot. So here in this region, the state with low value entanglement and low value of magic. These states are close to classical state. So they are extremely simple to be simulated, and we have no problem with that. Then there are here state with high value entanglement and low value of magic. And then this state we have seen before. So states that are so we have states that can be realized using or approximated, well approximated using only stabilizer operators. So with Clifford operators. So we start from stabilizer state. So we have no magic. We made the Clifford circuit. We can create entanglement, so we can arrive to a very high value of entanglement. But there is so without magic or with a very low value of magic, if we can add such a theory. On the contrary, we have in this other direction. Let's say, okay, we have a high value of magic and a low value of entanglement. Say, okay, so these states are hard to be simulated because we have seen now that we discussed all these things that are hard to be simulated. In reality, no, because this state can be simulated through tensor network. So this tell you that still magic is not really the final answer to explain why there is a quantum advantage. For sure, allow to explain something like that for the Clifford circuit, but there is still a problem. The two difficulties of states that are very difficult to be realized with a classical computer are this state here, state with high value entanglement, high value magic. This is extremely hard. They cannot be simulated well with Clifford circuit because Clifford circuit they are far away. Tensor network does not work well in this region. And then this is the huge problem. So what is the characteristic? If there is a single characteristic that characterizes this set is not known. It's still an open question. If you have an idea, feel free to suggest, to discuss, to write a paper because it's completely new. So we do not. So now there is some suspect that there is a new form of magic that is called non-local magic. So a magic in which you remove the local contribution. It seems to be that it can work, but the problem is still open, and we don't know exactly if this works well. But okay, before to do this, so I probably jumped too far because so making this plot, it's a way I quantify the magic. So this.
You know, there's an example. Is the walls there
Here.
Easy. So are there examples of circuits where you have states where you have high entanglement magic, but still you can simulate that?
I don't know if there are examples like that, to be honest. So for example, if you want, there is something that where this. So okay, this is a little bit more complicated than what we discussed. We have seen when we measure the entanglement that you take the eigenvalues of the density of the reduced density matrix, and then the entanglement is associated to the phenomena entropy, the reduced density matrix, like sum over I lambda minus log 2 over lambda I. But you cannot. So since you have this set of operators, you are not forced to limit yourself to study this function, but you can take this distribution. Imagine that you have two huge subdimensions. So you have a huge number of lambda I. This is a distribution function of numbers. And then you can study, and then you can see, for example, that in these two regions, okay, when the entanglement is close to zero, there are only few of them that are different from zero, and all the other are zero or very close to zero. Here is interesting. They follow a Poissonian distribution in this region here. So when they have, there is no, when you create without entanglement without using the T-gates, and instead I wrote a paper about that, and here instead you follow a Gaussian distribution.
You mean the lambda?
The lambda. Exactly. The distribution of the lambda.
So you have a Poissonian distribution with the higher.
Here I have a Poissonian distribution. Here you have a Gaussian one. No, it's not a thermostat, but it's a way. So you, for example, let's say we are very far, but this kind of entanglement is easy to be destroyed. This kind of entanglement here is extremely resilient. So if you take Metropolis algorithm, the Metropolis algorithm is an algorithm that is for everyone, so to explain a little bit. So how it works, the Metropolis algorithm is case. So you have your system, you make it by partition, and then you imagine you evaluate the entanglement. Then you made a unitary transformation here, a unitary transformation here, UA, UB. One of the two can be also the identity, but unitary transformation. And obviously, means since this one acts only on A, this one acts only on B, it does not change the entanglement in general. But then what you do, then okay, you do this, and then you start to do, you rotate these things, and then you create a transformation that can change the entanglement. And then you see what happens. If the entanglement is increased, you discard with a certain probability. That depends how much the entanglement is increased. If the entanglement is lower, you accept always. And then you go in this way, because so you the fact that when you go up, you accept a certain probability is to avoid local minima. Because if you have a situation like this for the entanglement, you want to arrive here. But if I arrive here, then I cannot never go up. I'm completely frozen. So I need to have the possibility to go up. So I do this. So you do this with. In this case here, you can destroy this. So it means that with 100,000 random operation, you completely destroy almost everything. Here, no. You're after million or billions of operators, so you still are on the same value. So there are these things connected to this paper. We wrote this paper on 2017, 16, 17, long time ago. So that's so the difference of the state that we took is that the state was generated with without the gate, so Clifford gates. So we started from zero. We made a random circuit of I don't remember 1 million of gates, but Clifford circuit, and then the amount of entanglement that you create here with Clifford circuit and here with T gates is statistically the same. Since everything is random, there is a fluctuation, but there is a fluctuation. So it can be that one case is greater here than here, and the other case is the opposite. I was saying, okay. Yeah. So let's try to quantify a little bit better the magic, because the number of gates is not. So obviously, if you know what is your circuit, it's easy to say, yeah, what is the number of T-gate, but if I give you a state, yeah, it's how to say that you have to reconstruct the circuit that obtain with the minimal number of T-gates is impossible. And so let's start to discuss two measures of magic. And so one is a geometrical interpretation, and one is a standard entropic one. So the geometric interpretation is the robustness of magic. A robustness is a way to measure a quantum resource that we introduce only now, but we can introduce even before, because the robustness, you can consider robustness of entanglement, robustness of coherence, robustness of whatever you want. What is the concept of robustness? So imagine that you have a state rho, and then you have two free states, in our case, free for magic, so stabilizer state, but you can consider separable states, so free for entanglement, whatever you want, and you call it this one tau and sigma. These are, so the idea is that I try to find the minimum number R, the minimum value R, for which rho plus R tau 1 plus R, this is only for the normalization of the density matrix, is equal to sigma. So my idea is that if I have my state and I start to increase the noise, and the noise is created by a free state, in our case, stabilizer state, I increase until I destroy completely the magic and I obtain a stabilizer state. What is the minimum value of this? Mean over R. Obviously, it's trivial if rho is separable, R is 0, because it's trivial. But instead, if rho is, so there is a lot of magic, this means that I have to put a lot of noise inside. This is, so advantage and disadvantage of this expression. Huge advantage. Works for pure state, mixed state, whatever kind of state you want. This is not only for magic, also for entanglement, also for coherence, for discord, for everyone. So if you have a resource theory, if you have a state, and you take two separable states, obviously, then you have to minimize all possible tau state tau and sigma. That is the problem. So this is the advantage that can be applied everywhere, always. So it's the point is that the minimization is a nightmare. Since there is no way to decide, or at least that you don't know exactly the state, but not in general. What is the correct tau and the correct sigma that you can use? That means that this minimization is extremely complex. We were able to find a way to evaluate this robustness for the W state, because we need, we were writing a paper about this non-local magic, and so we need the reduced density matrix obtained by W state, and we use these things. In that case, we have some symmetry in the state that allow us to find solution, but however, is a nightmare. The point, so advantage you can apply everywhere. Disadvantage is extremely complicated to evaluate. Even for a very small system, it's very hard. I remember that there were some Japanese that made some numerical evaluation, and they were able to find the largest, so the largest system that they were able to quantify magics was 8 spin, running for days for a super powerful computer. They were unable to reach 9. It is the amount of problem that you have. On the other hand, there is a stabilizer Renyi entropy. Okay, just we have the stabilizer in entropy is conceptually the same idea that we have seen for the von Neumann, the same idea that we see for the coherence. Just so we want to study an entropy connected to something that is connected to the magic. What is the problem? So if okay, let's do step by step. So imagine that I have a state, say psi, and then I have a complete set of state of stabilizer state. Imagine that we have n qubit, so we take a complete set of stabilizer state. And then I create the probability pi I, it is modulus of t. Oh, okay, sorry. So this is the quantity that I want to study. Okay, this again, as before, there was the eigenvalues of the reduced density matrices. This is a distribution, and we can evaluate the entropy. So one can say, okay, we can evaluate the von Neumann entropy of this quantity. We can write down pi sum over I log 2 of pi. You can do it, but this is not a measure of magic. Why? Because for a strange property of magic, you can prove it that there are states that are not stabilizer, but for which this quantity is 0. So this gives you the problem that this quantity does not work well. Unfortunately, you can overcome this problem. So we never talk about the Rényi entropy. So Rényi entropy can be considered a generalization of von Neumann entropy. So in a von Neumann entropy, we always have sum over I minus lambda I log 2 of lambda I. But in the Rényi entropy, instead we do something different. So we do density matrix, the Rényi entropy of order alpha of density matrix rho is minus the log of the trace of rho to the alpha, and this here there is 1 minus alpha. It is possible to prove that if you do the limit for alpha that goes to 1 from above, you reconstruct the von Neumann. If you take the limit of S alpha rho alpha that goes to 1 plus, this is the von Neumann entropy. Okay, so the idea is that, okay, this does not work, but some Rényi entropies instead works. So if it takes alpha greater or equal to, and then I write 1 minus alpha log over 2 log 2 plus sum over pi to 2 alpha. For alpha greater or equal to, this p square I already put here, so no. Here, to already put here. This quantity measure, so again, you can immediately understand why this kind of distribution tell you how much magic there is. Because if you have imagine that you have your state psi is a stabilizer state. So at this point, you can write down so you can change eventually the basis and find out 1, the stabilizer state of part of the basis, so this become 1 and all the other become 0. And so this trivially goes to 0. Instead, if this is impossible to do, this quantity is clearly different from 0. What to say again about magic? No, I don't know. So,
here,
here, this one,
yes.
any base made by stabilizer state.
The entanglement entropy of the
for no, this distribution. So this is exactly this one. This is nothing else the trace of this. Yeah. Yeah. Yeah.
The entanglement entropy can that entropy is 0. That means
if the entropy is 0, means that there is a stabilizer. So there is a one state in the stabilizer set that is the state that we take it. Because there is one coefficient equal to 1, all the other will be 2. Yes. Last thing that I was forgetting. So this expression is the definition of the stabilizer in entropy, but to be honest, is not really used when you make the evaluation. I was forgetting this point is important because you can prove it. This is one of the work of Sham 2 years ago, no, 3 years ago. They prove it that this expression here, you can write down the same way, like 1 minus alpha log 2 of 1 over 2 to n, sum over all Pauli strings of psi to alpha. So, what is, again, exactly as we said before for the robustness, advantage, disadvantage. It's a way they are all the opposite of the robustness. Advantage, they are relatively easy to evaluate. So in doing a very simple algorithm without making any particular strange hypothesis, you can arrive to close to 20 spin. And if instead, if you use a tensor network approach, you can arrive also to around 100 spin. If you have a very good computer, something more, but start to be tricky. And then start to be tensor network, make approximation, and you risk to discard too many things. But okay, you can arrive, you can also overcome 100 spin. Very good. Problems, you need the pure state. Does not work for a mixed state. So obviously, you can evaluate. No one forbid you to evaluate this quantity for a mixed state. What you obtain is not a quantity that is directly related to magic. So that's the problem.
That's different than this one, or
No, it's the same. This is the same.
Or like those are stabilizer states, no?
So, this one, yes.
Doesn't matter.
No, because stabilizer state, because this is 1, then you have to make the sum. This is the same. If it's the same for all the Pauli strings. So way you are, because since each stabilizer state is associated to n different Pauli strings, it's a way you are only reordering the Pauli string. So each single contribution is a reorder. So they prove. Exactly.
When that is max, that is quantity is maximum.
This quantity,
like you know to which states is quantity.
So I think that there are studies about that. For qubit, there is a form. I don't remember the name of the form, but there is a form. So, but I really don't remember what it is. So, but it's something, so for sure has to be less than n, because the magic is less than n, but I don't remember what it is. I think it's around 0.6 for the number of cubes.
What does it mean? Which state?
I don't remember the state, so you can check it. No, from one qubit, it's easy. No, you apply, no. This is the maximum for a single qubit. This one. You apply t to it. That's give you the maximum. Or zero or any stabilizer state. Yeah. So for one it's easy. Then for the other it's a little bit more complicated. Okay, I think that is enough. And I don't know. I don't know if this is the approach to give you the maximum magic. I think so. But I think that you can. So using so you're doing the idea that you do T gate on the first, then T gate times Hadamard on the second. Yeah, then this allow you even to put even more magic. So if there is something that is not so trivially linear.
You know what? Is there a potential relation between this quantity for some alpha with that and the actual amount of T gates?
No. So in general, no. This is not something on which I work. So it's. I know that there are people that are studying the maximum amount of magic that is quantified, but since I'm
apply only one thing. I get every time the same.
Yes. So the amount of, so for one qubit, that is simple. So conceptually, magic is that how many T gates you need to do. So since with one qubit you can do a lot of tricks. Yes. So, but moreover, take into account this. So that if I want to apply T to a different kind of a different state, no? So for example, T2 plus. Yeah, but T2 plus is nothing else than T Hadamard 0. Hadamard does not increase magic, so it's T. And the same, so this is in for one qubit in which, so the things become a little bit more complicated when there are two or more, because there are CNOT that are not completely local operators, because it's not act on two different qubits. Then this makes it more complicated to find the maximization, but for one qubit it's relatively simple. Okay, that's all, and thanks for that you stay here for the four lessons. It was a very pleasure to give a lesson here.